In this video we'll do an energy density calculation, which is joules per kilogram. Energy density is the joules per kilogram of material, or fuel you could call it. So here's something I found on the internet. I didn't check whether it's a reliable source or anything. Probably not. Doesn't say .edu or anything like that, but anyway, that's what I'm using for this quick example. So it says chemical symbol for palladium. There's its details. It decays by electron capture to rhodium-103, emitting X-rays with 21 kilo electron volts of energy. So we'll verify, see if that's true. So first of all, we need to find the energy released per nucleus of fuel. Okay, so we'll write our reaction first. The nuclear reaction would be palladium 103 plus 1 electron, because it says electron capture. That's how it decays. Makes rhodium 103. Okay, plus it gives off X-rays, so we'll just say it gives off, like when it says gamma radiation, it could actually be X-rays, but gamma is just the, I suppose, blanket term for radiation given off during nuclear decay. So when I say radiation in this context, I mean electromagnetic radiation. So yes, traditionally X-rays aren't quite as high energy as gamma rays, but they're much of a muchness. This one happens to have gamma rays with that much energy, which happens to be an X-ray. So don't get too caught up with that. It's giving off radiation with that much energy. Okay, we can treat cancers by utilising that energy released. So how do we find out how much energy it releases if we didn't know this, or to compare versus that? So here's our first step. First we find the atomic mass units, AMU. So we can do that from this table. So we'll have a look, see if it's got everything that we need. Palladium 103, so we've got to look up. It's, remember, all elements are listed in order of their number of protons, called their atomic number. So 46, and it's not there. Okay. So that's a problem. We can't use this table to find palladium's mass. So therefore we need to go onto the internet and type in palladium 103 AMUs, and it will come up, and Wikipedia will be fine because it's just a, it's a reference value, so you'd assume it's fine. So here's the website that I loaded earlier. Just scroll down, list all the isotopes of palladium. 103, here it is. 102.906087. This little number in the brackets is your uncertainty. It tells you about it later on, but just ignore that. So I'll just grab that actually, it would be easier. Palladium 103, it was this value. There we go, the mass of an electron, I'm sure is in our table. There we go, 1 electron. There we go, and rhodium 103. Again, it's actually not in this table. So back to the internet. So you type in rhodium 103 AMU and it comes up. Again, the Wikipedia page, it lists all the isotopes. 103, here it is. We're ready now. And gamma, it doesn't have any weight. It's got no mass because it's electromagnetic radiation, so we ignore that. So that's good, that's first job's done. Now let's just convert to kilos as our next step. So we know that, I'm just going to give myself some more room here. We know that 1 AMU, so 1 AMU equals, now I actually can't remember this, it's 1.6066 I think, by 10 to the negative 27. I'll just check 1 AMU to kilograms. Yep, so let's just use 1.6606 by 10 to the negative 27. So we can use Suzanne rule to convert that. We know that 1 AMU is 1.6606 by 10 to the negative 27. Of course you don't have to use Suzanne rules, otherwise you could do it. It's just the way I'm doing it. So we know that 102.906087 AMUs is how many kilograms? So calculator, let's do 1.6606 by 10 to the negative 27 times 102.906087, and then you would divide by 1, so I'll skip that, don't need it, and there we go. So we've got 1.7, and use quite a few decimal places. And there we go. That's how many kilograms in 102.906087 AMU of palladium 103. Again, you do the same thing, use Suzanne rule for the rest, so I'll just do it quickly. This is the AMUs, 0.000549 times 1.6606 by 10 to the negative 27. There we go. Now of course there's quicker ways of doing this, to be honest. I'm just trying to make it as clear as I can, but I mean you could have just added those two and multiply it by this value to get the kilos, but yeah. Next one, so 102.905504 times 1.66 by 10 to the negative 27. Oops, no, that's not it. 1.6606 by 10 to the negative 27. There we go. I'll just grab that. Okay, next thing, now we've got to find the mass defect. So mass defect, that means the mass that we lose and gets converted to energy, so that's going to be the final take the initial, which would be this, take away all of that. Okay. So we'll do that. I've already got that stored on my calculator. Okay, so I'll take this and take away the sum of these two. So 1.7088584 by 10 to the negative 25 plus that mass 9.116694 by 10 to the negative 32, close brackets. And now I know that the mass defect, and it's got a negative value, which is good because it's final take initial. We know for nuclear reactions to release energy, it has to be heavier before it is than after. Okay, because some of the mass gets lost, well not lost, but it gets changed into energy. So I'm glad we got a negative answer. There we go. So that's the difference between after and before in kilos. Next thing, we need to convert kilograms into energy. So that's where we use E equals mc squared. So the mass that we lost is this. In fact, don't worry about the negative sign, it's just not important. Just indicates that we lost mass. So there we go. That value times c, which is the speed of light, 3 by 10 to the 8, and that value is squared, so the whole thing squared. So let's type that in now. So again, we've already got that answer from our previous calculation, times 3 by 10 to the 8 squared. So 9.5, and so we can actually just grab that. So there we go. That's what it equals. So we've just found the energy released per nucleus of fuel. Okay. Right, so now we're going to use that and keep going on the next page. So there's that many. Oops, actually I made a mistake here. It's not kilograms. It's energy. That was kilograms times the speed of light squared gives us the energy, so that's joules. So therefore we know that it was that many joules per nucleus. Okay. Rightio. Now we want to know convert to joules per kilogram of fuel. Okay, so going back here, here's how much fuel we used in kilograms. Okay, so be very careful at this point. That's the fuel that we used, that many kilograms. This kilograms was just how much was lost from going from the fuel to the products. Okay, so we need to use these values here. This is the kilograms of fuel we used. Okay, so we went, this nucleus was this much kilograms. So we can include this value as well, because it's probably better, instead of just saying per nucleus, we might just, it's per nuclei of fuel, basically. So we'll add these two together. 0.70885848 by 10 to the negative 25 plus 9.116694 by 10 to the negative 32. I know it's not going to change this number by much because this number is tiny compared to this one. It's negative 32 versus negative 25. Okay, so it's like, 100,000 difference. No more. Over 1,000,000 times different. But anyway, you'll see. See, we virtually get the same number we had before, but it's still important to do it fully. So there we go. So that's how many kilos of fuel that we used. Okay, so therefore we got this much energy from our nuclei, which is this many kilos of fuel. Okay, so continuing on, if we want to work out what it is for 1 kilo, then we just make this 1 kilo and solve this using Suzanne. So let's do that. So it's this times this divided by that. So if you do that, I'm going to do it a bit trickier way, just to save myself a bit of time. There we go. So that's 5. Again, I'll just copy it, be easier. And there's our energy density. .58 by 10 to the 11 joules per kilogram. So that would be a fully complete example of finding out joules per kilogram. If you're doing, say, nuclear fission or fusion, you can compare that to, say, how many joules per kilogram coal gives out to show that it's way, way more energy per kilogram, way higher energy density. So that'd be a good little thing to compare. In terms of us, though, what did we have to compare? It said 21 kilo electron volts of energy, which means per nucleus, so we have to go back a step actually. Back to here. So we'll grab this. That was the joules per nucleus. And there's a claim that it should be this much. 21 kiloelectron volts of energy per nucleus. Okay, so how do we compare joules and kilo electron volts? So, first thing, 1 electron volt is 1.6 by 10 to the negative 19 joules. That's a constant. So now we can just put this number over here and then work out how many electron volts that is. So we'll do 9.53302086 by 10 to the negative 14 times 1 divided by 1.6 by 10 to the negative 19, and it gives us 595813 will do. electron volts. So what's that? Well, if it's kilo electron volts, 1 kilo electron volt is 1000 electron volts. Okay, because kilo means 1000. So you could again do Suzanne rule, but you could, if you're good, you can just do it in your head and work out that it'd be 595.8 kilo electron volts. So hugely different to what that source claims it is. So what do you do about that? Well, you need to go back, first of all, check your calculations, see if you did those correctly or not. And if you can pick up an error, maybe I made an error on the way through, maybe you pick one up, you'd have to redo it. Otherwise, you'd have to look for why it's claiming that it's so much less than what you calculated. You may be able to find a reason, you may not, but it's something to definitely dig deeper into. And this is the perfect example of why you don't just take whatever you read as being correct. You should always verify with your own calculations, and it improves your understanding of the physics as well. Okay?